This is a supervolcano that could lead to a continent-wide disaster and erupts every 600,000 to 800,000 years, causing massive destruction. Yellowstone is known as one of the most famous geothermal hotspots in the world and is no stranger to geological activities. However, a recent extraordinary and eerie discovery has put the entire region on alert. Late at night, the park shook, and the calm surface of the famous Yellowstone Lake rippled. Initially, this was thought to be just a minor tremor, but it was actually the beginning of a larger series of quakes. Seismic events led to hundreds of earthquakes occurring in the park over 2 days. Preliminary investigations indicate that these seismic activities are not random, and such movement could lead to a major disaster, as the earthquakes increase fears of a massive volcanic eruption. The large sequence of earthquakes in Yellowstone could be a precursor to a possible supervolcanic eruption with the potential to wipe out the entire continent. Residents are fleeing for safety due to this terrifying event. Yellowstone supervolcano has the potential for massive destruction, and if it erupts, it could create devastation on an unimaginable scale. The public and the scientific community are deeply concerned as this region, once known for its serene beauty and natural wonders, now faces a significant threat due to a possible eruption. On August 29, 1870, Yellowstone turned into a horrifying sight for a 30-year-old man. Army Lieutenant Gustavus D. was on an exploration mission in the Yellowstone area of the Wyoming Territory when he climbed Mount Washburn, located above the Yellowstone River. Looking south, he noticed that a portion of the Rocky Mountains was devoid of mountains. Only hills surrounded a vast forest basin that appeared to frame the dawn. According to him, this great basin was the massive crater of an ancient volcano. The lieutenant was correct. Yellowstone is indeed a volcano and not an ordinary one. The United States' oldest and most famous national park sits atop one of the largest volcanoes on Earth. However, Lieutenant D was wrong about one thing. The Yellowstone volcano is still active and dangerous. Supervolcanoes are completely different from normal volcanoes. Scientists use the term supervolcanoes to describe extremely powerful and loud eruptions. However, there is no universally accepted definition. An eruption that ejects more than 240 cubic miles of pumice and ash in a single event is considered a supervolcano, according to the U.S. Geological Survey. This is 50 times larger than the famous Krakatoa eruption of 1883, which killed over 36,000 people. Supervolcanoes flatten mountains, destroy life for miles around, and change the climate on a global scale. Humanity has not yet witnessed a supervolcano eruption, but such eruptions could put all species at risk of extinction. Scientists have managed to reconstruct the characteristics of such volcanoes. Initially, hot steam rises from the Earth's interior and melts rocks just below the surface, forming a large magma chamber. This chamber is filled with semi-solid rock and gases like carbon dioxide and water vapor, gradually raising the ground above. Over thousands of years, the magma accumulated in the chamber creates cracks in the ground. When the pressure in the magma chamber is released, dissolved gases erupt suddenly. This is similar to opening a soda bottle after shaking it. According to Bob Christensen, a researcher with the U.S. Geological Survey and one of the pioneers studying the Yellowstone volcano in the 60s, when the surface collapses and the magma chamber empties, the area above sinks into the ground. It leaves behind a massive caldera, a large crater meaning cauldron in Spanish. At the hotspot that formed the Yellowstone caldera, numerous eruptions have occurred over a period of more than 18 million years. The eerie lunar landscapes seen in the Snake River Plain are the result of massive lava flows stretching across southern Idaho, Oregon, and Nevada. These calderas were formed as the Earth's crust and the tectonic plate above it were pushed southwestward despite the hotspot remaining stationary. Have you experienced an earthquake at Yellowstone? Even if you deny it, the likelihood of a small earthquake occurring while you were there is high. The Yellowstone region experiences an average of 1,000 to 3,000 earthquakes annually. Most are too small to be felt, but there are exceptions like the major earthquake in 1959. Yellowstone is located in the Intermountain Seismic Belt, which includes Montana, Wyoming, Idaho, Utah, Nevada, and Arizona. This region is known for its geysers and hot springs that can be felt from north to south. Two of the recognized surface features of Yellowstone are the active volcanism beneath the park and the earthquakes that form along fault lines. During earthquakes, a mixture of tectonic and volcanic forces stretches the rock to breaking points, releasing energy rapidly as seismic waves. Earthquakes in Yellowstone help maintain the hydrothermal activity of Old Faithful and other geysers. The earthquakes keep the plumbing system of these natural phenomena open, preventing them from becoming inactive. Mineral deposits can seal off small cracks and channels, blocking the flow of hot water to hot springs and geysers. However, in most cases, people do not feel earthquakes below a magnitude of 3.0. Structures are only damaged in earthquakes of magnitude 4.0 or greater, while the ground in Yellowstone can crack in seismic events of magnitude 6.5. Earthquakes of magnitude 6 are rare but do occur. The most famous and tragic earthquake in the Yellowstone region occurred in 1959. This 7.5 magnitude earthquake caused an 18-mile wide landslide and was felt over an area of 600,000 square miles. It destroyed a popular campground crowded with tourists. The southwest Montana Hebgen Lake earthquake on August 17, 1959, was the second largest earthquake the continent has seen. The aftershocks of this earthquake, one of the largest in U.S. history, can still be felt. Hebgen Lake, a large artificial reservoir, stretches miles westward along the modern Madison River Canyon. Just beyond the site of Highway 287, at the head of the canyon, lies the Hebgen Dam, completed in 1914. The waters of the Madison River, renowned for its famous fly fishing, flowed into and out of the lake before the earthquake. The Madison exited the dam through an outlet. The Madison Range Canyon, heading toward Ennis, featured steep slopes covered with rocky outcrops and dense forest on both sides of the valley. Before entering the broad Madison Valley, the river descended from a height at the foot of the canyon. Rock Creek Campground was a popular resting area for tourists visiting Yellowstone National Park at that time. The initial tremor lasted more than a minute. Within seconds, as the earth slid down along the fault line, it left behind a 20 feet vertical bare wall of earth. Shortly after the massive earthquake, a piece of loose material from the north-facing slope of the canyon broke off and rapidly fell into the valley, smashing trees and violently hurling large rocks downwards. This material traveled several miles downstream from the Hebgen Dam. As the Madison River flooded the canyon behind the slide, the debris formed a new natural dam at the canyon's base. It swallowed trees and campers, setting the stage for the earthquake. Hebgen Lake was already in a precarious position when it was large. Waves surged over it. The residents of Ennis had to leave their homes in fear that the dam might collapse. The night was filled with terror, and scattered families fled in the darkness, those who could reach higher ground. The newly formed Rose Lake swallowed campsites and cars, while others trapped under the rising water screamed for help. Long and terrifying hours passed before dawn, and it took days to learn who survived and who did not. The final toll was 28 dead, with 19 more believed to be buried under the slide's debris. Authorities evacuated hundreds of injured from accessible but elevated points. Roads and bridges damaged by the earthquake were rebuilt, and the debris was cleared. A large section of the highway was reopened within just a few days, and repairing the Hebgen Dam took only a few weeks, a process that was managed within Yellowstone National Park. The earthquake caused changes in the park's most visited thermal features, including the Old Faithful geyser. Within 2 to 3 years after the earthquake, the eruption interval dropped to 65 minutes. But later, the average eruption interval of Old Faithful increased to 74 minutes. Sapphire Pool, a relatively calm hot spring in Yellowstone's Biscuit Basin before the earthquake, began to spout up to 200 feet high. These eruptions destroyed the biscuit-like formations within a few days. Steamboat Geyser, the tallest geyser in the world located in Yellowstone's Norris Geyser Basin, awoke from its 50-year slumber in 1961. The once tree-covered slope surrounding the Madison River is now draped in gray. Pools of water at the base of the earthquake project from the lake's surface as a monument to the largest Yellowstone earthquake since the 1980s, which occurred on March 30th. The 4.8 magnitude earthquake in 2014 was centered 4 miles outside the Norris Geyser Basin and was felt in parts of Montana and Wyoming. Yellowstone has an extensive geological monitoring system, but this system is largely unnoticed by tourists. Earthquake swarms are common in Yellowstone. The University of Utah, which operates 26 seismograph stations throughout the park, typically records more than 100 small earthquakes a day in dense areas, referred to as swarms between Old Faithful and West Yellowstone. Approximately 2,000 earthquakes were detected during the winter of 2010. Scientists can record data with the help of this comprehensive monitoring system to better understand the subterranean geology around and beneath Yellowstone. 3 super eruptions have occurred in Yellowstone. The most recent took place 640,000 years ago and was 1,000 times larger than the 1980 Mount St. Helens eruption. 57 people lost their lives in Washington. However, scientific calculations indicate that the numbers do not fully reflect the extent of the chaos. The ash column from the Yellowstone eruption rose about 100,000 feet high and formed a debris blanket stretching from the western United States to the Gulf of Mexico. The gray pyroclastic flow clouds in the air are dense, toxic mud. Superheated rock and gas, up to 1,470 degrees Celsius, swept across the terrain. A thick, hot mass hundreds of meters long, once a lush area, melded and filled like asphalt falling from the sky. All the valleys were filled by the impact of this eruption, and this was the least violent part of Yellowstone. An almost twice as powerful eruption occurred 2.1 million years ago, creating a crater the size of Rhode Island. In between these events, about 1.3 million years ago, a smaller but equally destructive eruption occurred. The planet must have felt the effects, as gases rose into the stratosphere and combined with water vapor to form fine sulfate aerosols, reducing the amount of sunlight reaching the Earth's surface and possibly causing a volcanic winter. Some scientists believe that our species' DNA indicates a volcanic winter, following the eruption of the Toba supervolcano in Indonesia about 74,000 years ago, which may have triggered a global cooling period that nearly wiped out humanity. This eruption might have reduced the human population to just a few thousand individuals. Supervolcanoes can be violent, but what they leave behind is only a thin sense of desolation. Erosion, glaciers, and minor eruptions, the most recent of which occurred 70,000 years ago, have contributed to filling the Yellowstone caldera with lava flows, and the remaining traces have been hidden by ash. The quiet forests become hard to notice due to the cumulative effect, unless you have an extraordinary view like D or are guided by a geologist. The island of Santorini holds an explosive secret. It continues to be affected by volcanic eruptions to this day. Beyond the Yellowstone caldera, nutrient-rich soils give life to the park. Primarily lodgepole pine trees dominate, and grizzly bears and black bears feed on the nuts produced by whitebark pines. Naturally, the terrain is full of trout. Without the heating effects of hydrothermal springs at the bottom of Yellowstone Lake, there wouldn't be such abundance in the rivers. Geysers, mud volcanoes, and other hydrothermal activities create many wonders on the planet, and half of the world's geysers are in Yellowstone. Hydrothermal features are constantly changing. Temperatures and behaviors are observed as steam clouds and emissions emerge in the forests. These steams are strong enough to cause the death of bison in their vicinity. Despite their volcanic origins, hydrothermal features in Yellowstone change regularly. The park had not been studied for a long time. After federal investigations in the late 1800s, Francis Joe Boyd, a doctoral student at Harvard in the late 1950s, admired the thick layer of welded, heated, and compressed ash. This formation indicated the presence of recent pyroclastic flows. In 1965, Bob Christensen discovered two separate eruptions and determined the location of the third with his colleagues the following year. They used potassium argon dating to understand that the three eruptions resulted from three distinct events. All three eruptions left behind massive calderas, but the most recent one completely covered its remnants. While working with his colleague Bob Smith on Peel Island in the southern arm of Yellowstone Lake in 1973, he noticed some trees on the shore were half buried and dying. He had done some work in the area in 1956 and planned to return to the same dock, but it was also submerged. What happened in 1923 prompted park personnel to place reference points along different routes throughout the park. Smith's curiosity led him to re-examine these benchmarks. According to his decades-long evaluation, the valley on Sierra Hill north of the lake had risen about 30 inches. However, the water level at the bottom of the lake had not changed, as if the northern part of the lake had risen, causing the water to pour into the southern part. The earth was trembling. There was life in the volcano. Smith published his findings in interviews with Yellowstone in 1979, referring to the living, breathing caldera. By 1985, the land had subsided again, heralding mostly small earthquakes. Smith and his colleagues exhausted all possible means to see what lay beneath the park. The size and potential of the underground volcanic system gradually emerged by analyzing the propagation of sound waves produced by the earthquake. Researchers found that a large hot rock cloud, inclined about 60 degrees to the northwest, rising from the Earth's upper mantle and with its base about 400 meters below the surface, fed the magma chamber. Small earthquakes release hydrothermal fluids to the surface, increasing the heat entering the chamber, reducing the pressure inside the chamber, and causing the ground to start sinking again after the 1985 earthquake swarm. Yellowstone dropped by as much as 8 inches over a decade, then began to rise again more rapidly. Since 2004, some parts of the caldera have been rising at a rate of nearly 3 inches per year. The surface continued to rise despite an 11-day earthquake swarm that began in late 2008. Doomsday rumors quickly spread online, and fears of a massive eruption grew. Will it erupt again? An eruption is almost inevitable. The 1991 eruption of Mount Pinatubo in the Philippines led to the deaths of 800 people, but this might be a smaller event. Meanwhile, after weeks of grumbling and spewing ash, the Hunga volcano delivered the most powerful lightning display ever recorded. The underwater caldera near the small kingdom of Tonga erupted with immense force on January 15, 2022. The Hunga volcano ejected 2.3 cubic miles of molten rock and evaporated enough water to fill 58,000 Olympic swimming pools. As a result, tephra, which is composed of evaporated salt water and lava fragments and volcanic gases, reached a height of 36 miles. This eruption, which nearly reached space, astounded volcanologists. Initial measurements revealed a massive ring of lightning growing about 180 miles from the eruption's epicenter. Volcanic lightning is a phenomenon known since ancient times. Young Pliny wrote about it during the eruption of Mount Vesuvius. In the event that occurred in 79 AD, lightning could be seen. However, Alexa Van Eaton, a physical volcanologist from the United States Geological Survey, and lead author of a new paper on the Hunga event, notes that no one expected to see an electrical discharge with a diameter of 280 miles. Van Eaton found that the eruption produced 2,600 lightning strikes per minute, the highest rate recorded to date. This is twice the number of flashes per minute recorded by NASA during a storm observed in the United States in 1999, which was 993. Van Eaton and her team tried to understand this extraordinary storm by reconstructing how particles of smoke drifted in a volcanic gravity wave. Kadu Shumi from Ludwig Maximilian, University of Munich, Germany, states that it created the perfect storm. The world's active volcanoes are under direct observation. Scientists rely on data collected from other monitoring networks to understand the timing of ongoing eruptions. Luckily, a U.S. weather satellite captured a photo of the Hunga eruption, allowing us to observe how the cloud grew. The lightning detection mechanism on the satellite detected only sparse flashes. Listening to the radio allowed Van Eaton to track the lightning ring. The only sound lightning makes when it strikes is not just thunder. Sometimes it pulses. Van Eaton says that this pulse is created by electrons moving along the plasma channel, generating a strong electromagnetic signal. This signal appears as both visible light and a bright flash, which can be detected from thousands of miles away. Ground-based lightning detection networks and Van Eaton with her team collected radio waves from the Hunga eruption and meticulously combined their data to map the location, intensity, and timing of over 200,000 lightning strikes. The researchers attribute the unprecedentedly high number of lightning strikes observed during Hunga to the large amounts of hot, salty water ejected into the sky. Location data supports this theory. Additionally, the presence of gravity waves from the Hunga eruption is noteworthy. These waves result from the movement of a volcanic cloud composed of hot volcanic gases, ash, and evaporated water. Within the volcanic cloud, the hot gases and steam rapidly cool in the upper layers of the atmosphere, forming ice crystals and small hailstones. When these particles collide, they generate static electricity, a process similar to lightning formation in a typical storm. However, the addition of volcanic ash particles known as tephra during volcanic eruptions adds a unique dimension to this process. Van Eaton and her colleagues note that the sharp leading edges of gravity waves create ideal conditions for lightning production. As small particles are pushed upward by the force of the gravity waves, larger and denser particles are pushed downward. This movement facilitates the formation of separate charge regions, allowing for lightning formation to correct the imbalance. This event is an explanation of a complex phenomenon that has baffled meteorologists and volcanologists, but many questions remain unanswered. As Van Eaton mentioned, although the lightning ring seems to die down at one point, the core suddenly fills with thousands of flashes,